So this is a screencast answering the standard. I can calculate the fields for lines and planes and their effect on charges and dipoles. So I didn't do a problem from the book because I just had to address the solving issue. So I just kind of drew this arbitrary situation similar to the one that I did for the very first screencast. So I've got an infinite plane A on the left with a charge density of negative 12.5 microcoulombs per meter squared, and then an infinite plane on the bottom of the density negative 11.5 microcoulombs per meter squared. So I knew that these would be, the one on the left would be acting in the x direction, the one on the bottom would be acting in the y direction, so I analyzed them differently, and then I was going to talk about how they'd affect the charge afterwards. So for in the x direction, I used the equation, the force felt on the electric field is equal to the charge density divided by 2 times epsilon naught. So then I simply divided the charge density by 2 times the constant, which I looked up, and then I made sure to have the units with the micro 10 to the negative 6. And that I solved to be negative 7.06 times 10 to the 5th newtons. And on the bottom, I did the same thing, but for negative 11.5 microcoulombs. So in any case, the charge felt, from the infinite field on the left, the point A, which I put in the middle of the screen, right here, it would feel more force from this plate because the charge density is stronger. So if this was like a 45 degree, this point would be feeling it like, if it was let go, it would shoot off slightly this way from 45. And this one is going to be working this way, so I just like the sum of those two. Let's see. If this were a dipole, like if it were fixed and the charges could rotate, then both of these were negative and directed this way, then the charges would spin, so the positive pieces of the dipole would be facing back this way, opposite of the negative, because it would just want to align itself to be attracted to those points.